And finally, in part C, we want to understand the local components of the Weil differential we consider in part B at rational places P infinity and PA's for particular functions x minus a to the n. And in order to see that, so in other words, let omega be a Weil differential as we considered, unique Weil differential as we considered in part B. And first, we want to observe that since a Weil differential, this Weil differential vanishes on the Adel space of its divisor plus f, particularly it also vanishes on the principal Adels. So since omega vanishes on the principal Adels, by proposition 1.7.2, we know that the Weil differential of the principal Adel, whose components, each components we have the same function x minus a to the n, is going to be 0. And we also know that this Weil differential can be determined as the sum of its local components at the places P of at the places of the rational function field. Let me denote this equal to by star. It will be enough to check how these local components behave at P infinite and at the rational places PA. And our first observation will be that the local components for at the places which are different from P infinite and PA, we have these local components as 0. In other words, for rational places which are different from P infinity and PA, this is obviously, this is not going to be 0 or pole of this specified function, so it has valuation 0. And indeed, this also shows that the local component of this Weil differential at P, which is different from non-P infinite and PA, P has this value as 0, because if we explicitly write the definition of the local component of a Weil differential, this is nothing but the Weil differential of the local Adel iota P of x minus a to the n, and this local Adel belongs to the Adel space of the canonical divisor, because Vp of iota P of x minus to the n is going to be 0. And otherwise it's going to be infinity, and this is always bigger than or equal to valuation of this canonical divisor. This is obviously 0. And if we know how these local components behaves for these places, again by this equation, it will be only enough to understand the local components at P infinity and PA. So that means we can simplify the equation start with this equal to, and let me denote it by double star. So just it remains to say, to observe how these local components behave by analyzing these values n, powers n. And first we see that whenever these powers are less than or equal to -2, we have valuations of the functions in the specified one under the valuations of discrete valuation maps P infinity. And this is obviously bigger than or equal to 2. And indeed, this is also equal to V minus Vp infinity of the canonical divisor 2p infinity. So that means this shows us the local Adel e to p infinity is the function x minus a to the n at the p infinity component is an Adel of the canonical divisor. So that means since omega vanishes on the Adel space of its divisor, by the definition of the local component of a Weil differential, we can conclude that it has also value 0. And again, in this case, by using the equation double star, we also get local components of Weil differentials at places, rational places PA for this specified function is 0. And if n is positive, we can also similarly observe that these local components for this function has value 0 because Vpa x minus a to the n is going to be n. For n is positive, this is positive, and this is obviously bigger than or equal to valuations of PA. PA is different from P infinity. This is 0. So that means these are also belongs to, if you consider the local Adel, who has the functions x minus a to the n at their P8 component. By the definition of the local components of Adel, since, and again, omega vanishes on its divisor, we get the desired equality. And okay, so that means it remains to observe what happens when n is equal to -1. So that means we want to understand how these local components of Weil differentials behaves for the functions x minus a inverse. And in order to understand it, first let me write this function as sum of the functions x over x times x minus a plus 1 over x. We can say this equal to by just making denominators equal to the right hand side. And we can also observe that the local component, the local Adel e to p infinity, so that means this is an Adel at p infinity component, we have this function and otherwise 0, is also Adel in the Adel space of the divisor of this Weil differential, minus 2p infinity, because for other, if you look at the valuations of this principal, that we always get infinity, but particularly if you look at the valuation at p infinity, we know that this is minus 2. So obviously this is bigger than or equal to the valuation of this conical divisor at p infinity. And this shows us, if we take the Weil differential of this function at local component, if you look at the local component of the Weil differential, omega at p infinity for this function, by the linearity of the Weil differentials, and by the fact that this function, since omega vanishes on the other space of p infinity, this quantity is also going to be 0, because we knew to p infinity x minus a is 0, because omega vanishes on the other space of 2p infinity, and this local other belongs to this other space. And again, from part B, since we know that this local component for the function x inverse, we have minus 1, this shows us indeed this quantity is also minus 1. And again, to understand the local components of Weil differentials at PAs, since we were able to determine this quantity as minus 1, we can conclude that for n is equal to minus 1, and by double star is going to be 1. So next week, our main motivation will be to understand how we introduce another description for an algebraic geometric course in terms of the local components of Weil differentials. Particularly, we will again consider some kind of evaluation maps, which will be chosen from the Weil differential space of a specific divisor in terms determined by, again, G and D, like in the previous setting of the AG codes we consider here, by looking at the local components of these Weil differentials for the functions 1. And we often need to use proposition 1.7.3 or the notions we consider here in order to understand what kind of codes, what kind of linear algebraic geometric codes we have, and how we can determine the parameters like we did in the previous description. And our final motivation will be to understand the relation between this type of AG codes and the AG codes we introduce in terms of evaluations. So this is all what I want to say for this week, and see you next week. Bye-bye.